In this lecture, we begin investigating data analysis and statistical methods with a brief introduction to descriptive statistics. In this lecture, we're going to start off with a brief introduction to statistical methods. We're going to focus mainly on descriptive methods and consider things like the meaning of statistics. We'll investigate ideas around distributions like central tendency, variability, and the shape of distribution. Then we'll consider data transformations, standardized scores. We'll see at least a simple procedure and why we might use these types of scores. And we'll finish up with some descriptive understanding of variable relationships, correlations, how things relate to each other, and then a brief commentary on data analysis. I'll provide a separate supplemental lecture, maybe a few short videos on some computational examples. It's useful to situate us in some definitions of statistics and discuss what we mean by statistics before actually getting into some of our descriptive statistics for this lecture. So first, we'll talk about statistics as a branch of mathematics dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. Like any branch, it is coming off of a tree of mathematics. So even though we may be talking about one subsection of mathematics, in statistics, it still relies on the core of all of math. Just as a side note, for those that are concerned about the mathematics in this course, as we've discussed earlier, we're doing some very elementary level mathematics. We'll do some addition, subtraction, maybe some multiplication or division, and we might even see a square root function somewhere along the line. But the concepts will be very simple, and we're not focused on the mathematics computationally, although we'll go over a couple of those ideas. But for those that are more interested, we have many other courses that dive into both the theoretical and mathematical underpinnings of the statistics you're going to learn just a little bit about in this lecture. With that said, statistics is a discipline. It's a discipline within mathematics. We deal with probability, we deal with uncertainty, we deal with variability. In statistics, we need to do a collection of data, and it's going to deal with the quantitative data and methods that we've dealt with through the semester. We're going to collect up bits of information and provide feedback to individuals through presentation. It's the theory, procedures, and methodology by which data are summarized. When I think about what statistics means, of course, it's things like mathematical theory and the statistical analysis and methods, symbols, and terminology that all goes around with statistics. But it's also part of science, right? We go through, we come up with a hypothesis, we collect data, we classify and organize that data, we conduct an analysis, which is actually what often people associate with statistical methods, and then we present that information. Here we're going to focus on the description and how to make sense of our data. So what you might think about this is as the process of what we do in methodology. And of course, our videos, what's useful to start with a pause moment. Here I bring up my research hypothesis. We've seen it previously about healthy eating. I have multiple groups, at least one of which is a healthy eating group. That's my treatment, and some comparison groups, maybe chocolate or no healthy snack. And we're going to see whether or not healthy snacks increase the performance on a mathematical assessment. In particular, here I've written for middle school children of 7th grade, as that's the sample of data I could collect, and I would generalize first to the 7th grade classes. So one of the reasons I bring this up is we are going to begin classifying and organizing the data around it, coming up with ideas around distributions and maybe relationships. We're not actually going to answer the direct research hypothesis with our descriptive statistics. We may give support or show evidence through classifying and organizing our data, but it'll be later on in inferential statistics when we get more into our detailed testing of a hypothesis. But for now, it's still very useful for you to have your research questions, your ideas, your hypotheses, so that you might think about how this applies in your research methods. We'll focus on more specific methods and procedures applied to understanding our data in the next chapter, in the next lecture. So when we talk about statistics, we also mean things like statistical analysis, and we'll learn some of ththose analyses like t-tests, analysis of variance and regression in our brief introduction to inferential statistics. But really, those methods and procedures we can think about as any function of a data set, any mathematical function that we're using. So that's another way that we conceive of statistics. We also think about statistics and quantitative research as going through experimental, quasi-experimental design, and non-experimental design. It doesn't matter which of our general design structures. If we are collecting quantitative data or have quantitative data in front of us from observations and non-experimental methods, we still use statistical models and statistical descriptions to help us explain our data. So in descriptive statistics, we're really going to focus on explaining, clarifying, describing, and summarizing our data. Descriptive statistics, we might define it as more formally the procedures and measures by which we describe quantitative data, our values or scores that we may have in our quantitative research. Descriptive statistics describe the distribution of scores or observations in terms of its location, dispersion, and shape. I will simply note here that what we can do both in descriptive statistics and later on in inferential statistics depends on what type of data we're using. If you recall from our measurement lecture, we describe data as nominal, ordinal, interval, and ratio. When data are more on the nominal side, where there's qualitative measures, but we still have things like frequency counts. For example, maybe you have a frequency count of preference of soda or type of favorite jelly bean. That's more of a qualitative measure. Versus when we get into interval and ratio level scales, where we saw the equal distance between our measures, where we have values like mathematics scores or temperature. We can do different things both with descriptive and inferential statistics. So we'll focus probably more on some of those data that are more of the inferential type of measurement. Operationally, we can present our data numerically in tables and graphically. Let's just go through some examples of descriptive statistics that we probably encounter in day-to-day life. These types of examples, they're things that we might hear when we're listening to a news station or when we're looking at videos online or discussing with friends and colleagues. It's the way that we speak about statistics, and this will sort of take some examples of descriptive statistics. You might be talking about average reading scores and their change over time. So here's an example that you might see if you were perusing some websites or articles about reading scores. So the average reading score for fourth grade students in 2019 was 220, which was lower than scores in 2017, which was 222. So there's things, we're just describing that. We can draw inference, we can think about this later on, but for now, we're just describing the statistics and we're just presenting them. Over 90% of respondents to a survey live north of the equator. So we may have conducted a survey and this is sort of just descriptive of the sample of data that were collected. The Dodgers had a .717 winning percentage in the regular season. So if you're a sports fan, you may be watching news and hear that they had this winning percentage. And really it's demonstrated here as a proportion. So we start to think about these ideas, how we might hear descriptive statistics in everyday life. Globally, almost 40% of cars built are white. In North America, that is actually decreased. So again, just describing an account. 85% of public high school students graduate on time in between 2017 and 2018. And about half of all Americans are ready to learn about cooking due to the coronavirus pandemic. So we're just describing. We're not making a claim behind these. We're presenting, we're describing or summarizing our data. And I think we all encounter these types of descriptives in our everyday life. So I'm going to try and move us from some of the intuitions we have around statistics to being a little bit more precise, give us some definitions, understand when we think about many of those descriptive statistic examples that we just went through, they're really about distributions of scores. A distribution of scores or observations is described by three statistical concepts. We're going to focus on measures of central tendency. You've probably heard the terms mean, median, and mode before. We're going to focus on those ideas. Measures of variability, maybe you've heard range, variance, or standard deviation before, and also the shape of a distribution. This will help us give more context to some of the language we use around descriptive statistics. There are different ways that we encounter data. Here I present some, you might consider it interval level data, also the same as ratio level data for presentation purposes. For example, test scores. Imagine you have a score on a test, on a final exam that's between 0 and 100, and here's a distribution of scores. Here's a data set. So we haven't done anything to this data. We haven't tried to collapse it. We haven't tried to present it in a table form or graphically. These are just raw counts. If I wanted to, maybe I'd have a person's name or identification next to each data point. But these are just scores on a test. So we can just think about our data that we're observing, and this is just in its raw form. Another way we might present data, more for nominal level data, things that we're just counting, might be if we ask people their favorite soda and we made a list. We put a list down the brands that people might suggest to us, Sprite, Coke, Pepsi, maybe there's other brands too that we could have put on here. But then we can just put a dash or a mark for each count. So then we could go back later, count them, and do some other things that we might do with nominal level data. But here's just what your nominal data might look like before you've done anything to it. A frequency distribution gives us a little bit of a shortcut. It lists each possible score as well as the frequency. We'll define that as lowercase f of its occurrence. So we have scores that are possible and then the occurrences. Now we see variations on the frequency distribution. Often it will contain things like proportions or percents. We might also see cumulative measures and limits. We're going to focus on the very basics of our frequency distribution. You will also see frequency distributions that have every possible score listed, and also those that have collapsed over scores for visual appeal and for understanding of the data more at a glance. Scores can be also graphically represented as a histogram instead of as a table. Frequency is indicated on the vertical axis and the values of the scores on the horizontal axis. The rectangles are proportionate to the frequency of the scores. We'll show you some examples of those. We'll start off with just a quick discussion of nominal data. Nominal data, again, are qualitative data. In this case, it's people's preference about soda. Also note this data is made up. I kept it to 100 just to make the frequency and percent match up very easily, help us identify and understand what's going on. With nominal data, there's actually not that much beyond this that we can do. It's people's preferences. We can identify the most frequent preference. In this case, we have identified here as Pepsi. And then we can see what percent of people selected each brand. We can see 12% people selected Mountain Dew, 22% Coke, etc., etc. If I went into a different sample and collected this data, I'd get a different percent structure. Percent is very useful here because if our frequencies weren't out of 100, let's say they were out of 9,042, we would get an idea of the raw value, but the percent tells us it in a standardized way. So in a way, percents are already intuitions around types of standardized scores. And we'll talk more about that later. The other thing I'll identify here is that when we talk about central tendency, we'll talk about the most frequent score, the mode, we'll come back to that. But in this case, with the data presented this way, we can quickly identify that Pepsi is the most frequent and the percent of people that prefer each type of soda. Here's another set of raw data. Maybe this is a dependent variable for me. I'm going to call it quiz scores. But this is a great opportunity for you to think about your hypothesis, even if the numbers don't quite match up to what you want. it's a good opportunity to try and put yourself in a situation where the dependent variable, the data that you're collecting, match up to these type of raw data. So I might just suspend a little disbelief and say this is scores for my mathematical assessment. Perhaps if I'm doing a measure or an inventory on satisfaction or happiness, I might say these are some sort of outcome of a scale score, just so that it helps me place myself in a situation where the content of this, in this case, some raw data that we're going to transform into tables and some graphs, makes a little bit more sense to you. And also it gives you an opportunity to be thinking more about your research ideas. Frequency distribution tables are going to help us understand and describe our data. We're going to observe the variable, which we've done. We've collected data, and now this is just going to help us interpret and understand the data scores that we have in front of us. So here we take all possible scores. In this case, on our quiz, you could have gotten a 0 on it, up to a 6, and the frequency. So 3 people scored a 6, 6 people scored a 5. Building a frequency distribution, you make a couple decisions. Here I've chosen highest to lowest. It just makes more sense for me to put the highest score at the top, the lowest score at the bottom. So 0 is at the bottom, the lowest score, all the way up to the highest score of 6. The frequency, remember, represented by that F value. It's the count of each interval. So again, we have, for 0, there were 2 instances. For 1, there were 4, etc. And we're going to place that number into the frequency column. This is really the start of a frequency table. We can expand the ungrouped frequency tables. This is one of those areas where I still expect you all to understand things like our scores, grouped versus ungrouped frequency tables, at least conceptually, and frequency counts. I'm expanding this for those that are interested. There's a lot that goes into things like trying to understand the best interval, whether to use an ungrouped or grouped frequency table, whether to add in cumulative frequency. So for example, when you look at the very topmost score for cumulative frequency, I see the value of 30. Because we're sort of adding up all of those frequencies as we get toward the top of score of 6. That's another easy way of knowing how many people were in this data set. The proportion of people in percent are linked to each other. Usually you present one or the other. And then cumulative proportion or cumulative percent tell you how many at or below fall in that category. So if we go across, we'll just go across score of 4. We can see that a score of 4, 6 people fell into that as frequency F. Cumulative frequency mean that at that point or below, there were 21 people. So scores of 0, 1, 2, 3, and 4, that's 21. The proportion of people that were scored a 4 is 0.2. The percent, kind of skipping one column over, is 20%. So those two are linked, proportion and percent. They're just different ways of stating the same thing. And then cumulative proportion is how many people, what proportion of people fell into that category, that score or below. So how many people scored a 0, 1, 2, 3, or 4, and that's 0.7. We see that linked to the cumulative percent of 70%. I'm not going to focus in on some of the expansions of grouped and ungrouped frequency tables. I'll show you the difference between a grouped and ungrouped frequency table. But this is more for your information and moving forward. There's a lot of combination of methodology and a little art that goes into creating a really good table as the expansion of scores increase, as we get a lot more possibilities. Here's another data distribution. I could have shown you the raw data. I'm just kind of skipping to the frequency table. This frequency table is constructed as a grouped frequency table. Instead of just having individual values, for example here, this is the number of credits someone has taken up to a certain point. So I've just binned them together for the purposes of describing and summarizing my data. This will also lend itself to when I wanted to develop a histogram and I want it to present well to others. More especially as long as I have the raw data separately and I'm not losing those actual data points, it really doesn't matter as long as I'm helping to correctly describe and present my data. So there's a lot of art and science, again, that goes into the development. We're not going to do that in this course. And if you get interested in our Intro to Statistics course, we do a lot of diving into development of tables. Our frequency tables, and we can see the little one up in the right-hand corner, is very useful for summarizing and organizing our data. But histograms are very practical when one wants to present the data that they have. So for example, we'll just kind of walk through what a histogram is again. I sort of mentioned it before and said we will come back to it. We can see that the scores are graphically represented here. We call it a histogram. There's a lot of different figures and tables that we could use. We're going to limit our discussion to just a few. In this example is a histogram. The frequency is now indicated on the vertical axis. We see it says frequency. It goes from 0 to 7. We see the numbers 1 through 7 displayed. And the values of the scores are on the horizontal axis. Here we've just displayed the average. So if you look at the little table in the corner, the topmost interval is 18 to 19. And we've just put that on our axis as 18.5, the average. So we see here, it's much quicker to see. If I were to ask you what scores were most frequent, you would be able to go to the boxes that represent 12.5 and 14.5. Well, also, if I were to say, does something look like it might be an outlier? That it might be a score that is a rare score or a score that doesn't fit the rest of the data. And quickly with our eyes, we see that 6.5, the scores that fall in the range between 6 and 7 rarely occur. As a matter of fact, 8 through 9 and 10 through 11 don't actually occur in our data set. So that little tail, that little outlier is very quick. We're very quick to pick that up visually when we have a histogram. So here's some raw data again. This might represent my math achievement scores. For you all, it may mean something else. If you're using your running example, we have scores that could range from 0 to 100, and these are actual data points. Instead of looking at them as raw data, trying to figure out what that distribution means, another example of a binned histogram, a grouped histogram, is presented to you. We bin this by groups of 10. So those that fall into each of those categories, each of those boxes, each of those rectangles going up from the x-axis along the y, we can see that in the score labeled 85, there were 7 values in that 10-unit interval. And we can go over and look and see that data. There was 3 80s, an 81, an 84, an 87, and an 88. There were 7 values that fell in the 80s. There was 1 value, a 92, that fell in the 90s. And we see that represented there on the distribution. This distribution you could think of as a distribution of scores or grades. And it's very helpful in this case to present it in units of 10. The really cool thing about this type of histogram is if instead of just having several cases here, we can look over to the side and see that we have 20 cases. Imagine you had 20,000 cases. Instead of having to look through all 20,000 pieces of data and their individual scores, you could have binned them in units of 10 and you would effectively be looking at the same type of histogram. These are helpful for presentation. They do not fully describe a distribution of scores. Again, histograms are excellent for presentation, but we still want to know more things about our data when we think about a distribution of our data. These two things together, the raw data and the histogram, really give us a lot of intuitions about our data, but we really want to know things like the location, the measures of central tendency, the type of dispersion we have, and the shape of our distribution. Measures of central tendency are points in the distribution used to locate the distribution. That is, we commonly refer to them as an average. The location is because we can use one value to try and locate a typical score across all of our values. The 3 most commonly used measures, the first is the arithmetic measure. The sum of all the scores divided by the number of scores. This is the mean. The mean is the mathematical average. The median is the point below which 1/2 of the scores lie. It's the middle point. And the mode is the score with the greatest frequency. This is used less often. It's just not as useful in some of our computational statistics, but it's still useful in this discussion of identifying 3 different types of central tendency. So let's just give an example of some data we've seen previously, just scores on our math test. They range from values of 49 to 92. We can see that the highest score was a 92 and lowest score was a 49. It's easier to begin when you're starting to do some analysis to just arrange these things. This is almost arranged just like we would a frequency table. Here I have scores just going from lowest to highest. I could have also arranged it and given an idea, different characteristic, given people's names. But here I just created a simple data set. Often we will form our variables into columns. So this is useful as we move forward from descriptives into inferential statistics, but we're still going to stay in the world of descriptive statistics for now. So measures of central tendency, what are they? For this data set, we have a mean of 73.85, an average score of 73.85. We have a median of 74 and a mode of 74. But really, we have something that's bimodal. That is, there's 2 modes. You can have multi-mode. You can have multiple scores that are the most frequent score. Let's deconstruct this just a little bit more. We'll start with the modes. I can just search through the data. Of course, I can do a function in Excel. I can use other software that I'll discuss later on, like SPSS, SAS, R. But you can also just kind of look for it. So we can see that the most frequent scores are 74 and 80. That's the mode. The mode is the most frequent score. Very easy to identify. It would be even easier to identify if this were truly in a true frequency table. So we would have just one score of 74 and it would say frequency of 3. Same thing for 80. So our mode is bimodal in this case, or you could call it multimodal. Instead of having one single score with the most value, we have 2 scores that share the most frequent value. The median is the middle, literally the middle. There's a lot more technical issues we can get into about the median, about calculating it and calculating it for tables. But for now and for us, we can just look at the middle scores. When the numbers are even like they are here, we see that we're falling in between 10 and 11. To find the middle, you can take 74 and 74 and divide by 2. So it's the score that falls in the middle. If this were odd, we would just take the middle point, the middle score. So the median is the middle, the mode is the most, and then the mean is our average score. I'm going to just go over a little bit of a mean value. This is an equation for a mean, and this is the outcome. So if we take a look at our little equation here, we have values of we have symbolically X bar, which stands for the mean. We have this idea of a summation. Summation, you may not have encountered that before. That's fine. Summation just means add things together. What are we going to add together? Values of X. So our equation says sum together values of X and divide by N, where N is our sample size. Well, we can see down here, if we were to take all of these values here, 49, 53, 59, all the way through 92, and put them in the numerator, you are literally just adding those things together and defining by the number of things. We have 20 total cases. So it would take the summation of this entire column and divide by 20, and that would give us, in this case, a value of 73.85. So just a quick summation. These are all 3 measures of central tendency. The mean is our mathematical average. The median's the middle point, and just for clarity, it's the middle point of our data when it's ordered. So in this case, we have it ordered from 49 to 92, going from the lowest value of 49 down to 92, and we just find the middle point. and mode is the most. Sometimes you'll see one value, like a score. In this case, there's two values, but it could be just one value. Sometimes you'll see a score. For example, there could be, if we had one more score of 80, then there would be 4 values of 80 and 3 values of 74. In that case, then 80 would become a single mode. When there's multiple modes, we can name as many modes as necessary. It gives us a sense of idea of the measures of central tendency: mean, the average; median, the middle; mode, the most. Although we're not taking a very deep dive into statistics, it's still necessary to go over a few definitions and discuss issues around symbols. So in our previous example, we started with a very simple symbolic example with the idea that x represented a variable. Specifically, we had x was the symbol for the variable called math test, and we assigned that at the top and gave it some values. We could have also called it y. And we'll see later on in our next video on inferential statistics, where a lot of these issues around statistics and parameters or around symbols of our statistics matter. So we use different symbols in discussion in inferential statistics, but also even in descriptive statistics, our definitions, our terminology, and the symbols that we use, it's useful to know those up front. A very specific way statistic is used is as a value that represents and is computed from the sample. So I go out, I collect some data, I do a small computation like we did for a mean, I get the average value, and that average score represents the sample. If I were to be able to collect up information on the entire population, instead of calling that same value a statistic, we call it a parameter. A parameter is a value that represents and is computed from the population. So you can an easy way to remember is S and S. A statistic is to a sample, as a parameter P is to a population. It's more than just a theoretical or philosophical difference, although it really is a meaningful philosophical difference and theoretical difference when we get into inferential statistics. There's also a small adjustment we sometimes make for our statistic versus a parameter, so it's useful to know when you're dealing with one or the other. So just as a recap here, effectively, a statistic is related to a sample and it's a computed value that represents that sample. A parameter represents the population and is a computed value that represents the population. They are very similar, almost sometimes identical in computation, but often we make a couple adjustments, as we'll see in variances and standard deviations. We use different symbols to represent a statistic versus a parameter. So for our statistic, for the mean, you'll often see X bar. For our parameter, for the population, you'll often see that symbol, which is mu. Looks like a little U there, but it's called mu. The standard deviation we'll often see represented by an S when it's a statistic. And when it is a parameter, the standard deviation is a sigma. For variance, we have S squared, which directly relates to the relationship between the standard deviation and variance. And for our population parameter, when we have a variance, we just have that sigma squared. Our sample size, obviously a sample statistic, we use the lowercase n, and when it's a population parameter, the size of the population, we use an uppercase n. These are just a few of the key differences between a statistical symbol and a parameter symbol. Again, they basically mean the same thing, but they represent it for something different. The mean of the sample versus the mean of a population. You may see a few other examples through our lectures. And you'll see other symbols. For example, you'll see lowercase r for correlation, and we'll see a z-score, and it'll be represented by a z. And later on in our inferential statistics, we'll see a couple other symbols representing the name of the statistic. Now we're moving from measures of central tendency to measures of variability. So about our distribution, measures of central tendency give us ideas about where the locations are, the centermost points. Measures of variability are a description of the distribution's dispersion, how far across our scores spread. It's the spread of our scores. In contrast to central tendency, which are single points, these are going to represent intervals. It's a number of units on the scale of measurement. And we'll talk about several different types. The three most commonly used measures of variability are the range, the variance, and the standard deviation. The range gives the number of units on the scale of measurement to include the highest and lowest scores. This is typically a very unstable measure of variability. It changes. It's just a quick and rough estimate of the variability of our scores, the range of our scores. The variance is a mathematical computation. It's the average of the squared deviations from the mean. We'll go into this in a moment. Then the standard deviation is just simply the positive square root of the variance. So really, once we figure out what the variance is in context, we just take the square root of that to get the standard deviation. Again, we'll go into that in a moment. Just as an example, the range is the difference between the lowest and highest score. So R, the range, equals the highest score minus the lowest score. In our example, we can simply see that in our math test, the lowest score was a 49, the highest score was a 92. So we simply just take 92 minus 49, and our scores have a range of 43. It's also useful when reporting the range to give those kind of cap scores, to give those values as 92 and 49. So it's not really used that often. That is, somebody might report it, but doesn't have enough information to be of real value. It provides information about the pattern. It does not provide enough information about the pattern variation amongst the scores. The idea of variance and the mathematical computation of variance is really central to so many of our statistical models. Here are the symbols just as a quick refresher. Sigma squared is the symbol for population variance, and S squared is the symbol for a sample. So sigma squared is our population. S squared is a sample. Here are the equations. I'm going to deconstruct these equations for you to give you just some words around these equations. We have the mean of the squared deviation scores. The numerator is squared deviation score. The denominator is either the population size or the sample size. We have squared units in order to keep things positive and also to reduce bias. We talk about our variance as that on average, it's how much a squared score deviates from the mean. If we didn't square these values, the deviation scores would sum to 0. So mathematically, we have to do something in the numerator. This is not the only time I'm going to talk about variance. We're going to talk about it a few times. I'm going to do a computation. I just want you to this is just sort of your first look at the equation and a little bit of language around it. Now we're going to deconstruct it, and we're also going to deconstruct it in a computational video. Instead of tackling this equation all at once and trying to explain it, we're going to break it up. And again, we're going to do this twice. We're going to do this again more in a computational style. But first, let's get the language and the ideas around the deviation scores and the variance components. So to calculate out a deviation score, we take the distance of each score from the mean. It's just each value subtracted from the mean. That's this part of the numerator, just x, the variable, any individual variable, any individual value from that variable minus the mean. We also call it a location of a score relative to the mean. It's how far away you are from the mean. If you take any value and subtract it from the average, that's how far away you are from that average. These scores by themselves, if we don't do anything to them, will always sum to 0. The deviation score is defined as that numerator. Let me just pull it down. Let's remove the big variance equation and just isolate it. When we talk about deviation scores, we're just talking about how each individual element of a variable, how far away it is from the mean. And that's each value subtracted from the mean. So we have deviation scores, just any value minus its mean. The problem is if we were to sum all of those to try and do something with variation, it would all sum to 0. Any data set, for any data set. So we square those values. We call those values either the sum of squared deviation scores, or you'll see they'll call it sum of squares for short. They are the summation of the squared deviation scores from the mean. So we have those deviation scores from the mean, and we square those values and sum them. This is what you will see it sometimes referred to symbolically. Remember, the deviation scores just look like your value for a variable minus the mean. In the equation, the sum of squared deviation scores is the numerator. So let's make that go away and let's rebuild just that piece. So we take those deviation scores, we square them. So now we can calculate them as a sum, and they'll provide a positive result. So we have deviation scores, we square them, and then we sum them. That is the entire numerator of the variance. Again, we're going to do this again. This is just your first walkthrough of variance. In our more computational video, I'm going to walk through an example just so you can see what we're going to do ahead of time. We're going to take any variable x. We're going to calculate the mean. We're going to then take the deviation score for each value. We're going to square those values. Then we're going to add the values of those squared deviations. We're going to sum those values. We'll divide by n minus 1. That is our variance. We're going to do this again. This is in words. This is to show you the symbols. And what my expectation is that I separate out the supplemental computational work so that you can come back and forth and choose the pieces more efficiently that you want to review. So if you just want to go back to the computational video, which will cover this calculating variance, we'll come back to this slide again, and we're going to do this work for some simple data. So that way you can go back and forth. If you get these ideas, then you don't have to embed that in this video. We have highlighted the variance for the sample because that's what you're going to be computing most of the time is sample variances. And in the denominator, notice instead of n, it's n minus 1. So n is your sample size. The minus 1 is simply there to account for bias that occurs in sampling. If you want to know more for why we do that, that's a good reason to start considering taking more traditional introductory to statistics courses where we'll get into issues more about bias of samples. Statistics form a population parameter. The standard deviation in practical terms for reporting in descriptive statistics is very, very useful. It is the square root of the average squared deviations about the mean. That's a fancy way of saying we just take the square root of the variance component that we just went through. It is much more meaningful in a practical way because the units aren't squared. Large values of the standard deviation just mean that there's wide scatter around the raw scores of the mean so that, there's a lot of dispersion. We see a lot of scatter in our data. Whereas small values of a standard deviation mean that there's very narrow scatter, that those values are all pretty close to the mean. Computing this value, Fortunately for us, if you can compute the variance, all you need to do is the same steps as the variance. You actually just take the variance, and at the end we take the square root of that. And that's what our equation looks like. It looks exactly like the variance, except we've just taken the square root to get it back into the original units that we measured. Symbolically, it's just useful to note what the population standard deviation looks like. Here's our equation a little more formally. Notice that really the only difference that occurs is in that denominator. We're using a little bit different symbols, but instead of just taking n minus 1, small n minus 1, we're taking n for the size of the population in the denominator. And I'll just go on to I'll reiterate the sample standard deviation. The sample standard deviation is what we just saw. It's just the square root of our variance component. And again, we have n minus 1 in the denominator instead of n, little n for sample size. And we just subtract 1 to keep things unbiased. So that, and unbiased here just means that by making that slight adjustment, sample standard deviations will look a lot more like a population standard deviation would look like. Our standard deviations help us build our measurement scales for a given variable. They indicate the amount of dispersion on a distribution of scores. The standard deviation is in the original units of the variable measured, which makes it very practically useful in descriptive statistics. In any discussions that we want to have, it gives us the ability to say things like, if our math test has a mean of 94, so the average on a mathematics achievement test was 94. The standard deviation was 2. On average, scores were about 2 units away from the mean. This means that most people scored above 90. This is foreshadowing some issues in inferential interpretations, but also gives us some very practical understanding. With those two pieces of information, a mean and a standard deviation, I begin to know a lot about the data, regardless of whether I have 10 variables in the data that I'm interested in, or whether I have 1,000 or 1,000,000 data points. With just those two values, I begin to know a lot about the dispersion of my data. We're going to move to the general shape of distributions. There are a lot of different shapes and distributions that our data could take on. So it's much less important here to focus on what the exact shape is, but instead we really want to know, does the shape conform or does it come close enough to some theoretical shape? The most popular shape that we try to make things look like, or that we associate with some of our statistical models, is the normal distribution, which typically has a symmetrical shape. Two things about the normal distribution where we could deviate from it is, one is kurtosis, which is just a way of saying how heavy the tails of a distribution are. Are they different from what a normal distribution is? Skew is asymmetry. If we have a positive skew of a distribution, then many of our scores we have many low scores and fewer high scores. Whereas if we have a negative skew, we have much more high scores than we have low scores. So there's many high scores and fewer low scores. The classical bell-shaped distribution is the normal distribution. It itself can look a little different depending on two of the attributes of distribution, or two of the moments of a distribution. So in a normal distribution, when we have no skew and there's no kurtosis going on, more especially with the skew, we have our mean, our median, and the mode at the same location in the middle of distribution. You just might think of this, I kind of put silly here, a little turtle shell, maybe to help remind you of what instead of just bell shape, what a distribution might look like for a normal distribution. So the normal distribution, which we use quite often in our educational and psychological research, is really a family of distributions. It's not a single distribution. And some of the characteristics about it that we can change are things like the mean and standard deviation, the middle score, the average score, and the dispersion. So instead of just thinking of this as one We can think of this as many types of distributions that basically look the same. That is, they're symmetrical distributions with bell shapes and basically look like this distribution. But they can be more narrow or more broad as well. Here's just a very simple example of two distributions overlapping each other. The one that's a little taller, they're both normal distributions. They actually both have the same area under that curve. The one that's a little bit taller has a narrower distribution and has a smaller standard deviation. The one that's a little bit broader has a broader standard deviation and has a little bit more dispersion. So one of the characteristics we can change about our normal distribution is its variance. Another characteristic we can change about our distributions is its location, its mean. So these are actually identical distributions, just shifted up and down the number line. So A has a mean of 10 and a variance or of 2, and B has a mean of 20, and C has a mean of 30. We see all the variances are the same, which mean all of the standard deviations are the same. It would be the square root of 2. All we've done is shift that up and down our number line. So if we were to overlap them, they would look identical. So one of the things we can define a normal distribution is not only by its variance, as we saw in the previous slide, but by its mean. There can also be a difference in both the mean and variance. These are both still normal distributions. The first one has an average score of 20, a mean of 20, with a variance of 5. The second one has a mean and an average score of 30 with a variance of 1. So there's a difference in both the mean and variance of those distributions. Just as a note, the larger your variance or standard deviation, the more broad, the more dispersion there will be in your distribution, and the smaller your standard deviation or your variance, the smaller the dispersion there is, the smaller the scatter there is in your distribution. When a distribution is not symmetrical, doesn't have that nice bell shape or turtle shaped curve, we call it skewed. When we have a positive skew, that means that most of our scores are all clustered together, usually around a lower score relatively speaking, and there's a few higher scores that are pulled out in the tail that cause the tail of that distribution to go out. From a perspective of central tendency, if you recall, when our distribution is symmetrical, the mean, median, and mode are all at the same point. Now we see that they're a little bit split up. The mode is least impacted. That means it's going to be hanging out in the cluster of those low scores. And because the tail has been pulled out in the high values, toward that direction, the median is going to be pulled out. And the one that's going to be impacted the most is the average or the mean. It's going to be pulled out the furthest from our distribution. So we'll typically see in a positive skew also the mode, the median, and the mean in that order toward the positive. Just like our turtle can help us remember the symmetrical shape, our dinosaur here can tell us a little bit about skew. We see that the dinosaur shape is similar to the skew, and the direction of the tail matters. We see that the tail is going off from the negative direction, from the central area toward the positive. So that's what a positive skew, a positive tail pulls you out with a few high scores in that direction. Just like our positive skew, the negative skew is the exact same thing, but in the opposite direction. So we have clusters of high scores and then a few low scores pulling out the tail in that direction. Again, our dinosaur's facing this way, with its tail going toward the negative direction or the lower direction. We can see that the skew of the distribution is being pulled in that direction. So our mode is still the one that's most in the central location where those clusters of high scores in. Then impacted second would be the median that we pulled out a little bit further, and the mean would be most impacted toward those fewer low scores. That means that our mean is most susceptible to a few scores that are in extreme conditions. That does not mean that the mode is more valuable. Often you'll see people report the median as a more stable value when there's a few high or a few low values. Those extreme values, what you hear is outliers. One might use a median instead of a mean. Very rarely is a mode reported for those reasons. But also you have to check what those outliers mean, whether they're practical issues or whether they might be just anomalies in your data set. But often you will not see a replacement for the mean in some of the analysis. You'll see a determination of whether or not this skew is significant enough, a big enough skew, that we don't believe that we could use a statistic that would require a normal shape without skew. Here's just a recap slide. When our distribution is normal, there's no skew. The mean, median, mode are all in the same place. When there's a slight positive skew, we see that the mean is impacted the most, then second the median, and third the mode in the positive direction. When there's a negative skew, the mean is pulled out toward the negative the most, then the median, and then the mode. And that's how the shape of the distribution interacts with some of our issues of central tendency. It's also sometimes how we can know, besides other tests, how we might know whether a shape is negatively or positively skewed. So in some ways, I think it's also useful just to really quickly review what real data kind of looks like. So these are histograms. So these are going to be constructed, and I just left them without values. But these are just histograms constructed like we did previously. So real data doesn't always look that pretty. Here's just a difference in central tendency, identical histograms with just the mean shifted. So we can see the two means are different, but the shape of the distribution is identical. Here's what histograms look like. The one on the left has a little bit of variability. The one on the right has a lot of variability. So less dispersion and more dispersion. That's what it would look like as a histogram. Symmetrical distributions can look a little like the normal distribution, like the one on the left. And the one on the right is just a flat distribution. That's not necessarily going to be useful for a lot of the type of analysis we'd like to do. But technically it's still symmetrical, but it's not a normal distribution. Skewed, we have skewed to the left and right. These are in histogram form. So you'll see these if you actually get to doing some real data analysis. You'll see sometimes those skews pop up, and it's like that little tail being either pulled to the right or pulled to the left. I mentioned kurtosis. There's two types of kurtosis. I'm just going to mention them very briefly. There's two types. One is leptokurtic. Leptokurtic is when there's not enough information in the tails. You can see there's a difference in the amount of the information in the tails. There's more information in the middle of the distribution than in the outward ends of the distribution. When we have too much information in our tails, our distribution kind of looks flat, or there's just heavy in those tails, the far ends of the distribution. Plateau, you might think of for platykurtic. So it's kind of a flat distribution. For elements of our shape of distribution, we're going to leave it at that. So you've gotten a little bit of what a normal distribution looks like, and when it's skewed, and when it's kurtotic. We're going to take our knowledge, and now we're going to transform it into our standard scores, some transformations that we might do in correlations. In educational and psychological testing, we often need to transform our data. We have sets of scores that we can transform into called standard scores. There's actually different types of standard scores. We're just going to focus on one, the most popular type. So standard scores can simply be obtained by transforming our data. The unit of measurement is the standard deviation, and the score is expressed in standard deviation units from the mean. That's what we're transforming our data from raw scores into standard scores. The type of standard score we're going to talk about is a z-score. It's the most frequently used transformation. So we're just going to use the symbol of the lowercase z to represent scores. Transform scores are useful here because we can have measures on different tests or dependent variables, and we can transform them to the same scale so that when practical, when logical, they're on the same metric mathematically, we can compare those values from different sources when it's appropriate. This is all still in the descriptive statistic world, but this is one of the key components that will move us eventually into some of our inferential statistics. With all of that talk about shape of distributions and the bell-shaped curve, the standard normal distribution, if you've heard that term used, are our z-scores. They are the standard scores that we've transformed. They have some specific properties. When you transform your raw data into standard scores, into z-scores, the shape, the general shape from the original distribution stays the same. But two critical elements change. The mean is transformed to be 0, regardless of what the original values of your data were. The mean will be 0, and the standard deviation and variance will both be 1. If the variance is 1 and we take the square root of that, we still get the value of 1. So now our z-scores for the distribution of our new standard scores, they have in general a bell-shaped look to them, which is as bell-shaped as the original data. So if you had a little bit of skew, you'll still have a little bit of skew in this data. And they're defined by the characteristics of having a mean of 0 and standard deviation of 1. Another useful thing when looking at our standardized scores is that we get an idea of the percent of cases under a portion of the curve. So we can see under each of these 8 portions, we've broken our distribution into 8 different portions, the area under the curve. So for example, when we go from 0 to +1 variance, 1 standard deviation, or 0 to -1, we see about 34% of the cases fall within 1 standard deviation of the mean. That also means that 68%, almost 70% of our data is approximately 1 standard deviation away. Another way of simply saying this is that most of our cases, when we have a standard normal z distribution, when we have our transformation, the bulk of our cases, almost but not quite, 70% of our cases will be within 1 standard deviation. That tells us a lot about the distributions of our data and what impact dispersion has. It also helps us relate our data set to other data sets. To determine standard scores for our standard normal distribution, our z-scores, we're going to transform from a raw data set to our z-scores. We do this by moving the distribution by the mean and squishing or stretching by the standard deviation. In words, our standard scores is just taking your observed score and subtracting the mean. And after you've done that, you're going to divide by the standard deviation. In symbols, that looks like our z equals, our z is our z-score for our standard score, is equal to the observed score x minus the mean of x divided by the standard deviation. I'm going to go through other examples in our computational example, just a simple second example, but here I just took this example from our textbook to relate it back to this lecture. So we have 2 tests. So suppose an experiment is being conducted and there are 2 dependent variables, performance on a math test and performance on a science test. So our first dependent variable is our performance on a math test, and our second dependent variable is performance on a science test. If a subject in the experiment has a score of 78 on the math test and a score of 92 on the science test, which is the better performance? Well, our intuitions just kind of go to, well, 92 is higher, so that should be better. But that is not necessarily the case. We need to understand the distribution of scores. So the distribution of math test scores has a mean, an average score of 76 and a standard deviation of 4. The distribution of our science test has a mean of 94 and a standard deviation of 6. Let's just go to an intuition here before we even do the calculation. You score a 78 on a math test and the average score was 76. You did better than the average score. You score a 92 on a science test, you are a subject in your experiment, and you scored a 92 on the science test, but the average score was 94. So you did less than the average. So right there, our intuitions start to kick off and say, well, on the math test, I did above. On the science test, I was below the mean associated with each of those tests. Also, our standard deviation gives us a little bit of information. The distribution of scores in the math test were less than the distribution of scores in the science test. I can see that because the standard deviation of 4 for the math test and a standard deviation of 6 for the science test. Let's go ahead and do that computation. We're going to take the observed score, subtract the mean, divide by the standard deviation. So for our math test, we take the observed score of 78, The mean was 76. We subtract that and get 2. We then divide by the standard deviation of 4, and our value is a positive one, is positive 0.5, which is in line with our intuitions when we looked at the difference, just the raw difference between the mean and the observed score. For the science test, we take the observed score of 92. We subtract that from the mean of 94, which gives us a -2. We divide by that, the -2, then by the standard deviation, which was 6. And we get a negative value in this case of 0.33. In this illustration, something we may notice is that we have both positive and negative scores. So technically, your z-scores can range from between positive and negative infinity. However, on a very practical note, the vast majority of scores will be between positive and -3. However, in interpretations for folks, this causes some difficulty for people. Some folks aren't used to seeing a negative score on a test. So there's all sorts of transformations you can do. Once you get a standard score, you can transform that into so many other types of scores. So one of the types of scores that you commonly see is we can just take and do a shift of 50 and maybe multiply by 10. That's a very common transformation. So I'll go ahead and show us what that looks like. The basic transformations we're going to do here is just a really simple transformation where we multiply and add. In this case, we're going to multiply our z-scores by the new standard deviation we'd like and add the new mean. So for our example, we're going to multiply by 10, a new standard deviation of 10, and we're going to add 50. So let's go ahead and do a really simple transformation. We're just going to multiply by 10 and add 50. So our new standard deviation will be 10 and our new mean will be 50. The reason again that we're doing this is because it's difficult sometimes to interpret negative scores. By shifting our mean over by 50 points and by multiplying by a new standard deviation, we get a new metric, a new way of looking at a test score. So if our z-score previously that we just calculated was a positive 0.5, we just simply multiply that positive 0.5 by 10, giving us 5, and add 50. Our new transform score for our math test score would be 55. We could do the exact same mathematics for our science test. So if we had previously a score of -0.33, we just multiply that -33 by 10 and add 50 and we get 46.7. Again, through transformations, we can create sort of any metric that we want. Our new metric has a standard deviation of 10 and a mean of 50. Even though it really has the same meaning, when you go to explain to someone that they had a standard score, a transform score of 55, and explain its meaning versus trying to explain a 0.5 as a z-score, it's much easier to discuss with a practitioner. In the literature, you're going to see a lot of different types of transformations. I mean, test publishers, sometimes you'll see things like a mean of 50 and a standard deviation of 100, which might be popular for some standardized tests. You might also see a mean of 100 and a standard deviation of 15 for things like intelligence tests. These are very common transformations that are done in the field, and they're all done for the purposes of interpretation. So when you see someone that says that there's an IQ score on average of 100, it's been transformed to be 100. So when somebody has a score of 115, it's actually the same thing as saying they had a standard score value of +1, but people don't want to hear they have a +1 or -1 IQ score, so that transformation is done. It's done the exact same way we just did this transformation with a mean of 50 and a standard deviation of 10. It's all for the purposes of interpretation, interpreting your scores. So far, we've really just been describing one variable, but now with a correlation, this is going to be defined as the degree of relationship or association between two variables. So instead of just a variable x, we may have a variable x and y. So instead of just a variable x, which might be our math test, we also have a variable y, which might be our science test. And we want to see how those two things associate or relate to each other. The extent of the relationship is shown through the distributions of scores that represent the two variables. The scores are made up of paired scores for a single group of individuals. So each person has a score on both values. We are interested on how scores covary, or we might say vary together. In the bottom right-hand corner is a scatter plot or scattergrams. We're going to see some more examples of those, but I thought it's just useful to show that here now. So when we think about correlation, I often find it useful to think about these types of scatter plots or scattergrams that we'll see in our text and in these examples. So since I've used math assessments and math achievements throughout the semester in one of my examples, so I may have my students in a 7th grade class, and they have taken some assessments, and I have grades for those students in a 7th grade mathematics course. So I might be interested as a researcher in looking at the relationship between the math grades of students in my 7th grade math class and their scores on some statewide mathematical achievement test. So researchers are interested here in how the scores in the distribution relate to each other, how they correlate. The relationship between two distributions of scores is based on how a change in one variable compares with changes in another variable. Our correlation coefficients, or our correlations have something called a correlation coefficient. We usually see this lowercase symbol of R. We also might hear it called the coefficient of correlation, and we'll discuss a little bit about Pearson correlation coefficient later on. It's an index. This R value, this correlation coefficient, is an index. It ranges from and including -1 to +1. So it's an index of relationship between two variables, and it can be any of those values. You can have a value of 0, a value of 0.5, a value of -9, as long as it's within that range of positive and -1. The greater the absolute value of the coefficient, the stronger the relationship is. We call that magnitude. A correlation of 0, there is no relationship. We say our two values are independent of each other. Values of plus or -1 are very strong. So an absolute value means that we drop the sign when we just think about the strength. So a -0.9 correlation is actually stronger than a positive 0.1 correlation. That brings us to what the sign means. So the sign of the coefficient plus or minus means the direction of the relationship. A positive value means high scores on one value are associated with high scores on the other. We also can think of it as low scores are associated with low scores in the other. So they're going in the same direction. If you have a positive relationship, then positive values, so for example with our math and our science test, if we have a positive relationship, as you see larger positive math test values, you expect to see positive larger science test values. A negative relationship, the minus sign, a low score on one variable is actually associated with a high score on the other variable. So if in our example, if we have math scores and science scores, if we had low math scores, we would expect, if there's a negative relationship, to see high science scores, and vice versa. Fortunately, instead of having to get into the complex algebra of some of our equations, there's a very basic correlation formula we can use. Our R value, our correlation coefficient, is equal to the cross products. So that means we take a standard score for our first variable times the standard score for our second variable for each person. Each person has a pair of scores. We take and multiply those two together. We sum them for each person. We go ahead and sum everyone total and divide by n. So for example, if we were looking at this from our perspective of our math and science test, everybody went and took a math test. Everybody went and took a science test. We have 10 people. For each person, I take their standardized all of their scores. So I've got a person 1 standardized score for math test and person 1 standardized score for their science test. I multiply those two together. Then I do the same thing for person 2, person 3, all the way from all 10 people. I sum those scores together. I add those scores together, divide by the number of participants, and that will give me my correlation coefficient. So relatively straightforward. We'd multiply two z's together for everybody and divide by the number of people, and we get our correlation formula. That's a lot easier than some of the algebraic equivalents. Just right away, you're not responsible for this level of equation. This is what we might do in an introductory course to statistics. instead of this course. So these equations I just show you as a reference point. Also, for those that get more interested, you can think about our correlations as variation, as the issue of different types of variance and covariance equations are all decomposed in here. And if you get more interested, just send me a note and I can send you to some other locations for more information. But again, you are not responsible for the more complicated algebraic equations here. So related to our correlations are our scatter plots, our scattergrams. This is an easy way to understand the association between two variables. Scattergrams or scatter plots, they're synonymous. They're defined as plotting the scores of the two variables. One variable is assigned to the horizontal axis x. The other variable is assigned to the vertical axis y. Each individual's pairs of scores is plotted as a point on the scale. And there are as many points as there are individuals measured. With our scatter plots or scattergram, when you have a perfect correlation, positive or negative, all of the points fall in a line. So for example, if we had a positive correlation, a perfect positive correlation of 1, we would see all of our values on the x and y axis create this line in our scatter plot. If it were a negative relationship, we would see it going the opposite direction. So in our positive relationship, it goes from the lower left to upper right. And in the negative, it goes from the upper left to lower right. We can see, for example, in the positive, the first scatter plot, that when we have low values of negative x's, we have low values of y. And when we have very high values of x's, we have very high values of y. And the opposite is true with our xy relationship. When it's negative, we see high values of y and then low negative values of x. And then when we have low values or negative values of y, we have high positive values of x. This is extremely rare, and as a matter of fact, it's almost always whenever you see this, when it's actually perfect, it's usually some sort of artifact of mathematics. Most of our scatter plots are going to be between plus and minus 1. Most of our correlations are going to be plus or minus 1. And what we see is that our points start to fall into some form of ellipse, some sort of non-perfect linear relationship. So a really highly correlated value may be a really tight ellipse, whereas as it becomes weaker and weaker, we see just more spread in those distribution of points, those scatters of points. And completely uncorrelated, we start to see things that almost look like balls or are just distributed very widely. Here's another set of examples. Height and weight, there's a positive correlation. We can see that the ellipse is the scatter there is not too much, and it's a relatively strong positive relationship. The relationship between the number of hours you sleep and how tired you are is a negative relationship. Again, not a perfect relationship. There's scatter in there, but we see the general negative relationship closer to 0.9-ish than closer to 1. Negative 0.9, sorry. And then eventually, hours of sleep and your shoe size really are unrelated in a data set. So we see that there's just general random scatter around there. So we tend to see things that look a little more like the height, weight, and tiredness than we do to see things in any sort of perfect relationship in our scatter plots. Our data really can take on whatever form it wants, so it's nice to see positive linear and negative linear relationships, or even maybe no relationship, but you also can have things like nonlinear relationships. Those things tend to have bends or curves in them. Even signal functions can occur in our scatter plots. It's one of the advantages of looking at your data. You can look to see, does it generally look linear? It doesn't have to be perfect, but does it generally look like a linear relationship? Just one last example to associate some values with our scatter plots. A moderate size correlation of 0.33. We can see that there's a lot of scatter going on in there. It starts to form some sort of relationship. As we increase to 0.69, we start to see more of a linear relationship form. At 0.98, it's a really good looking relationship. You rarely ever see relationships as strong, and at 1 we see the perfect line. Same thing for our negative values. At negative 0.08, we almost have no relationship there at all. At negative 0.64, we see the relationship start to strengthen and go the other direction than the positive relationships. At 0.92, we have a very strong negative relationship, and at negative 1, we see the perfect line of a negative relationship formed. I'll mention here, I mentioned it before, correlation does not necessarily mean there's a causal effect. It doesn't mean that the causal relationship exists between the two variables. In our little example here, we've seen before, there may be a third or other external factors influencing the scores. Correlation is just a mathematical computation. That's actually true when we talk a little bit about regression, leaning from correlation. Even when we're making more of a prediction, that doesn't mean that there's causality. That is a statement that you might believe a causal effect exists. Causality is a logical claim, a claim that needs to be supported well with a logical argument. Correlation is just a mathematical support potentially for a causal argument, but it is not causality itself. So regardless of causality, again, causality, we need to have a good logical argument. Sometimes that causal relationship helps us make things like predictions. So a correlation could be used in a prediction model. We want to estimate one variable from the knowledge we have about another variable. The variable from which one predicts is the predictor variable, and the variable being predicted is the criterion variable, our outcome. We can use an equation, a very basic equation here for our predictions. That is y equals bx plus a. Y is the criterion variable, it's our outcome. X is the predictor variable. So we're just basically taking x and making a prediction about y. In order to do that, we're going to adjust x a little bit. The way that we're going to adjust x is we're going to multiply x by a slope, which has, if you notice in the equation for the slope for b, it has the regression. And we're going to add an intercept. So our regression line allows us to predict values of one variable, our criterion, from another variable. In more complex regression models, you can have more complex predictors and other ways of predicting. The correlation between our x's and y's have an effect on the errors that we make when we're doing predictions. The accuracy of prediction increases as the correlation between the predictor or predictors and a criterion increase. So the relationship between x and y, if it increases, the prediction we make will increase. The greater the correlation, the smaller the standard deviation of those distribution of error scores. We call that the standard error of estimate. So the greater the correlation, the smaller the errors are. In a lot of our educational and psychological assessments, we use prediction all the time. We may want to predict achievement tests or as a criterion from an intelligence score as a predictor. But we see this in all sorts of regression models. It's actually one of the most popular types of statistical methods we use. With very few exceptions, our data analysis is done with our computer. You do it from your laptop or maybe on your iPhone, or maybe you're sitting down at a laptop, your work computer. But most analysis now can just be done right on our computers, and it's been that way for a very long time. Statistical software really just allows us as researchers the flexibility to conduct the analyses we want. There's a lot of flexibility. There's a lot of software out there. I would say the most common software that would be used, you've probably heard of SPSS, SAS, R, and Excel. Those are probably the four most common. There's other software out there for specific types of analysis. You may have heard of M+. You may have heard of S. You may have heard of people using Python. So there's a lot of other types of packages. SPSS, SAS, R, and Excel are probably the most common that you would encounter. I'm going to show you an example in Excel, and depending on the nature of our next lecture, maybe something in SPSS, but I'm not expecting in this lecture, we're not going to go very far into our statistical packages. I'm going to post later on a separate video for computational work. We'll do a little bit of work in Excel. So we're not going to go into any more of the details on computer software. And also in this class, we're only going to have a limited interaction with any of that software, and most of it will be with very basic packages in Excel. We've gone through, this is a summary, we've gone through our basic understanding of statistics, and a few times we've kind of redefined statistics and compared it with what we mean was a more formal theory versus in a very practical sense as a measure of a sample. We've compared that to parameter values. We've gone through distributions, understood the central tendency, variability, and shapes. We did a little bit about standard scores and analysis and why we might want to standardize. And then also, once you have standardized scores, why you might want to transform those for explanation. We also discussed correlations and relationships. Data analysis, kind of briefly touched on that, and I'll show you a little bit more in Excel as I've done in a previous video as a supplemental to this lecture. Considering the nature of these two lectures, the descriptive statistics and inferential statistics, we're going to wrap things up with inferential statistics, but we're going to give ourselves time for this information to sink in. And I will discuss that more in our inferential statistics lecture.